We were approached back in 2022 by Royal Martin, and they approached us about a panel repair line. But this one had a bit of a unique request in that they wanted to be able to repair panels that have been trimmed down to their final size. Repairing untrimmed panels wasn't really an option for them. Their process didn't allow for it. And they also didn't want to put every panel that they make through this line. So this allowed them to cut the panels to size ahead of time, grade out any panels that they didn't want to go to the panel repair line. The initial idea was to stop the panel. So we would take it out of our vacuum system and put it in an area that we could enclose the entire thing. Problem with that is just that you couldn't keep up with the volumes. If you stop the panel, you lose your throughput. So that was one unique challenge, was how do we contain this panel as it's moving? It was really up to the sales team to come up with a concept that the customer was comfortable with investing in. Really what that was, a lot of time in front of whiteboards, many meetings, sketching things out, involving engineering when we needed it, presenting those options to the customer, and ultimately landing on something very similar to what we ended up providing.
There was a fair amount of work that went into just understanding what are the criteria that we need to satisfy in order to make this thing work. So, for example, we built panel repair lines similar to this in the past, but the panels were all untrimmed, meaning they had a rough edge around the perimeter of the board. And so you didn't really have to worry about what was going on around that 2-inch edge around all the boards. But in this case, the ask was to be able to run trimmed panels. And so you introduce a whole list of challenges when you do that sort of thing, from having to present the panel very consistently and precisely on the conveyor, where we hadn't really didn't have to deal with that before. Understanding the characteristics of the putty and poly material that actually repairs the boards. And so before, it wasn't really in our scope to have a full understanding of how those behaved. But when you're responsible for making sure that that stuff cures properly, you better understand it well. And so we had to do quite a bit of research on particularly the poly product and understand, at what temperature does it cure? What type of materials will the poly material, release from instead of, stick to after it dries? So there's a lot of, preliminary background research and testing that we had to do to feel confident in the solution that we ended up landing on. A lot of credit goes to Dana Jacobson, who's now retired from Convey, a longtime engineer for us, and just a brilliant guy. He's the one that came up with the idea for the induction heating system. A lot of the concept was kind of his brainchild there.
All the projects at Convey, we break it out, project engineers, and then other engineers do individual sections. So the project engineer kind of oversees the whole project. That was my role in this particular project. I had the vacuum beltway, which integrated directly with the damming system. So it was me and Dana kind of butting our heads to get that to work together. Both the vacuum beltway and the damming system had to go at the same speed. They had to move the panel down the line at the same speed. If they don't, the belts on the side will move at a different speed, and then it'll actually peel away the whole process that we're trying to accomplish. And then it'll peel away the dam of the poly, and it won't heat up that side, and then they'll just spill over, and basically they'll have to reject that panel. So it was pretty intricate and pretty important that both the belts on the vacuum beltway, the repair station, and the damming system went at the same speed as it went down the line. In testing, we found that one of them was going faster than the other. We're like, why is this not working? Like all of our tests on the test bed, like just with nothing moving, our cure times were fast enough. So we would time it, how long it would take to go through, and then we would test on the test bench to see, like with the damming belt at the certain temperature, if it would cure in enough time going through there so we could meet our throughput. And then when we got to actual testing in the shop, we're like, why is this not working? Like it's not curing. And we found out after some slow-mo video that the the damming belts were moving faster than the panel, so it was scraping off our dam, and then it was causing a failure.
I think we were pleasantly surprised during the first iteration of the damming system, how well it worked, particularly the heating part of it. When we first tested it here in the shop, it worked really well. Just after a few days of fine tuning, we were able to get it to perform pretty well. But the real challenge came when we actually installed the equipment and began commissioning, because that happened to take place in the winter. And so ambient conditions were a lot different than when we did our initial testing. So because it's such a temperature dependent process, we found that our heating system just didn't have enough capacity.
On these lines, it's common that the panel stops. It has too many defects, so the router and the poly need to repair multiple sections. We found it was possible here. We knew we had some tweaking to do. But then once we got out to the field and started commissioning there, we just got feedback from the Royal Martin team, and they needed more heat because they were stopping the panels inside the damming system, and it was just cooling off too fast. So then Spencer and I worked to add those 3 additional heads per side, heating heads per side.
We had some failures on the steel belts that create the walls for the panels. Those steel belts failed pretty often when we first started this project. What would happen is the belts were supposed to stay tracked, and so there was a series of rollers, and these rollers were just, the ones on the end were crowned, which is a good method for keeping a belt tracked on a pulley. But the ones that were in between the head and tail pulleys were just flat. They didn't have flanges on them to keep the belt tracked properly. And so we ended up remaking all those rollers to put, a flange on the top and bottom. So that way the belt couldn't wander anymore. And so that was huge, because before we did that, the belts would, tend to wander, and they get right to the edge of the pulley, and sometimes they would go over it. And because it's a steel belt, it has virtually no stretch to it. So when it would kind of crest the edge of the pulley, it would start to develop rips. Once it was damaged and had a rip in it, it was just a matter of time before it was going to, fail all the way. The thing that was most new about this whole project was the inductive heating system. And so it's not new technology per se. It's fairly new to us. And so there was a pretty good learning curve as far as how that was going to work. What are the design characteristics that we have to watch for? So we partnered with Ultraflex Heating Systems, and they were a tremendous help in providing guidance on what to watch for and how their system was going to affect the other equipment that we had in the area. So one of the lessons we learned is, while we were doing startup, anything metal that gets within about an inch of their hoses or cables, or anything that was steel that was within an inch, would start to heat up really fast. And so we had these clamps that held down these hoses that supplied their heating system, and those clamps just melted into just a puddle of goo one day, because we didn't really know. And it just happened to be that those clamps, they were mainly plastic, but they had metal screws in them, and that were right in close proximity to these flex leads, and it just melted the clamps all up. So that was something we didn't really think about, didn't expect. So we had to go and make 3D printed parts that were different versions of those, that had all plastic fasteners that don't heat up. And so those are the types of little details that you don't think of all those, during the design process. You try to, but you don't get them all. Sometimes you just got to learn when you're testing.
I really enjoy collaborating with the customer. Just getting to see a different, the people that we're supplying, the different viewpoint on things. Because in our engineering team, we just see the product on our computer screen, and it's not very often that we get to go out and see it in process, or what these mill guys actually need. So it's really, beneficial to me, and I take it back to all my designs now. We're pretty fortunate with the people that we get to do business with. They're working families just like we are, providing for their families and everything else. So it's just really comforting to be able to go across the country, and we're both kind of working for the same goal, the same thing. And then on top of that, like, the Royal Martin team is just hands down one of the nicest people to work with in general too.
It seems kind of cliche to say it's a team effort, but for us, it's very true. And our commissioning team spent a lot of time out in the field. And I have to give a lot of credit to Royal Martin's team as well, because they were very committed to seeing this project succeed. We couldn't have done it without their willingness to jump in and help solve problems as well. So it was really a collaborative effort between us, our client, our sub-vendors that were a part of the project to get us across the finish line.
I think there are customers that we have the relationship with that we know that they're going to be in it for it to be successful as much as we are. And Royal Martin is really one of those partners.